Good morning, everyone. Based on where you are, it may be good night or good evening or good afternoon. So welcome to the CAD for Assurance webinar. This is the fourth webinar introducing our tools. And we are very happy to have two talks today. The first is from Professor Debdeep and his students, Sayandeep, on side channel. They already shared the slides here. The second talk is a very interesting name called Mimi. It's about hardware Trojan insertion automation. The talk is from Patanjali and from Jonathan from University of Florida, and the first talk is from IIT Kharagpur. So I assume that many of you have already attended the CAD for Assurance webinar. So, but for those who just joined this webinar for the first time, the CAD for Assurance webinar is sponsored by UF NELMS Institute, IEEE CEDA, IEEE Hardware Security and Trust Committee, Technical Committee, and by a few companies. So the key idea is to share the tools. We have so many academic tools that we published so many papers to supporting them, but while we're trying to use them, we always have so many issues. So we invited the authors of this tool to introduce those tools. Along with those webinars introducing these tools, we also have panels. We had the first panel on Zero Trust. We attract almost 200 attendees. And the next month, we have another panel on side channel analysis. So I hope all of you would also register and attend that panel. So with that said, I want to give the podium to Debdeep and his students to introduce their work and their tool on EXP fault. Maybe before that, Sroop, do you have anything to add?
No, thanks, you covered everything. I really appreciate the presenters agreeing to present today. And again, as you mentioned, the goal is to do academic dissemination of the exciting research activities going on in the field of hardware security, particularly with focus on developing CAD tools for assurance. That's the overarching goal here. So appreciate your interest. One more time, and thanks for joining today. Hope you'll see some exciting presentations from two sets of presenters, Sayandeep, Debdeep, Pallav Dasgupta, I think he's not here today, but Sayandeep, Debdeep are here. And then followed by two from University of Florida, Jonathan Cruz and Patanjali. They will give presentations on their tool. So thanks again to the presenters. So I will again thank to Dr. Jean for organizing everything. Appreciate the hard work. And also thanks to IEEE CEDA, particularly Amanda and Brooke, for their very diligent work to organize these sessions. So there are a series of them. As you mentioned, there are upcoming webinars as well as panels. These are highly popular events. So please do register ahead of time and attend. If you have any questions, feel free to get back to us. So with that, I'll hand over to Debdeep and Sayandeep.
Yes. Okay, good. So please check the chat room with follow-up information. And if you have any question, we have the Q&A at the bottom of the Zoom. Just type in your question. So we will answer that after the presentation. Debdeep.
Sure. Thanks, Yair, and thanks, Swaroop, and thanks to all of you for this invitation. So this work essentially is on an automated framework for exploitable fault characterization for block ciphers. And this work, as has been mentioned, is jointly performed with my PhD student, Sayandeep Saha, and also my colleague, Pallav Dasgupta, who works in the area of formal systems. So this work essentially is on what we call as fault attacks, which essentially falls into the category of implementation-based attacks. And as we know that side channel attacks essentially tries to kind of attack implementations and bring out that there is a gap between theory and practice. So if I take a classical crypto system where there is an encryptor, decryptor, and the eavesdropper wants to kind of understand what is a decrypting key, we know that mathematical ciphers are pretty good to protect against such kind of attacks. However, in the real life, because of the fact that crypto theory has got limitations, and because of the fact that side channels are leaked in the real implementations, whether we talk about hardware designs or software designs, even mathematically strong ciphers really leak in the actual world. So therefore, right, cryptography is not really a solution, but we probably need to understand the implementations and develop suitable tools, which is enormously challenging. So in this work, we try to address one of such threat models, what is known as the fault attacks. So we know that fault attacks have become growingly popular because of the various targets or surfaces, as we say. Like not only like you have got standard surfaces like symmetric key, public key, but you also have got other more like present day surfaces like from AI, or maybe when the crypto goes into automotive systems, or even it's implemented on cloud, or even in the context of what we called as post-quantum crypto. And the reason why, one of the reasons why fault attacks have become growingly popular is because of the means through which such faults can be created. So classically, we had techniques like voltage glitches and clock glitches, which has become even more powerful with tools like EM, lasers, and what we know as row hammers, which essentially has also tried to attack several software implementations of ciphers. So in order to kind of analyze against such kind of attack threats, we essentially need to develop our understanding of what we call as fault analysis, in which the adversary is allowed to inject faults into the crypto systems, and then we analyze the outputs to recover the secret key. So this has been shown to weaken even mathematically strong crypto systems, and therefore, right, and often doesn't even need high-end equipment. So we need to kind of develop suitable analysis tools. So one of the most popular technique for doing such kind of fault attacks are what are called as differential fault attacks or differential fault analysis, abbreviated as DFA. So in DFA, what we do is we take the plain text, we allow it to encrypt, and we get what is called as a fault-free cipher text. Now on another run, when we essentially give the plain text and when we are obtaining the cipher text, we try to kind of create perturbations inside our encrypting device and get what is called as a faulty cipher text. So this analysis tries to perform inspection or mathematical analysis of the fault-free cipher and the faulty cipher and reveals the secret key. So there are enormous amount of applications and like examples of where DFA has been applied for various kinds of ciphers. So classically, it has been applied on what is called as the AES, is essentially called as the AES block cipher. So in this particular case, what we observe is, or what we try to illustrate is that there is a fault that has been created, and the fault kind of gradually propagates across or along the ciphering path, and it creates very interesting, I would say, like interrelationships which are exploited by these attacks. So the current state of the art for AES shows that with one single fault injection, the key space can be reduced from 2 power of 128 to a paltry 2 to the power of 8 values. So here is a GitHub repository of an independent development of a DFA on AES with one single fault. So now what we want really is to test our given ciphers or given implementations for such fault attacks. And the interesting part is that we would like to develop suitable countermeasures against them. But then these countermeasures are very resource hungry and are costly. So what we try to inspect is we try to kind of identify what is the exploitable fault path or fault space. And if we are able to understand what are the exploitable faults, because all faults are not really exploitable, then we can develop precise countermeasures and therefore can create nice trade-offs between performance and security against such attacks. So therefore, we need to develop tools to essentially perform such kind of evaluations. Another very important point is that although there are, like a large number of block ciphers being developed, but manually it takes quite a large number of days or years even to develop optimal attacks for such kind of, or optimal fault attacks for ciphers. And nowadays there are too many ciphers, and we know that the reason we have got too many ciphers because we have got many applications. For example, recently in NIST, there's a call for lightweight block ciphers. The block ciphers are even promising even in the post-quantum world. So therefore, right, there are too many ciphers, there will be more ciphers, but it would be therefore motivating to develop a nice tool which can help us in doing such kind of analysis in an automated fashion. So we need a generic automation, we need fast, and we need also to be scalable so that they are scalable to modern parameters of the ciphers. So EXP fault is one of our efforts in doing that. So this particular tool essentially takes as an input a cipher description, which usually comes as the executable of the cipher, and also comes in the form of what we call as what is basically the the cipher description in certain graph theoretic formulation that we develop. We also take or parameterize the fault and what is called as a fault model, and then we try to kind of perform a fault simulation, and the fault simulation is followed by a data mining step, which essentially unearths certain fault properties, which are subsequently analyzed by some graph theoretic analysis to give us certain very important and interesting results. For example, it tells us whether a fault is exploitable, it tells us the attack complexity, it tells us the attack procedure, and also the required number of injections. So pretty much what is important from a fault analyzer or a tester of fault attacks. So we have essentially performed several case studies. Here is a quick snapshot of some of the important ones. For example, AES, Present, Clefia, these are standard ciphers. Interestingly, we could unearth an attack on a cipher called Gift, which essentially was not reported in literature at that point. So the proposed approach is essentially like we need to kind of represent the cipher. So we need to kind of formalize the cipher. And as we know that this particular attack of differential fault attacks is reliant on the definition of what is called as a state differential. So the idea is that you have got a clean execution of the plain text when there is no fault, and then you get a faulty path of this to get what is called as a faulty cipher. And every state you take an XOR or exclusive OR with the correct state to give rise to what is called as a differential or state differential, abbreviated as delta ij. So now we also need to represent the fault or formalize the fault. So we formalize the fault by using a tuple of state of injection, the width of the state, and most importantly, the width of the fault, that is the fault model. So for instance, the fault can be a bit fault, it can be a byte fault, a nibble fault, and so on. And also the location of the fault in the state. So with these parameters, we try to find out a suitable distinguisher. So the idea of a distinguisher is essentially trying to kind of understand the various differential states and try to find out whether the differentials are essentially exploitable. So therefore, the idea here is that the objective of these differentials is basically to reduce the key space of any block cipher or any cipher and come up with a filtered key space so that the actual key is a component or belongs to that filtered key space. So we need to kind of reduce the key space because otherwise the attack doesn't work. So then how do you define the differential, or how do you define the distinguisher? So in order to define the distinguisher, we try to kind of look into the various differential paths and then try to see that whether the differential essentially leads to a reduction in a metric. So the metric that we use to find out a suitable differential is a standard entropy measure. And we try to see that whether the differential's entropy is less than what it should be. For instance, in this classical example of the DFA for AES, as you can see here, that a particular state has been highlighted, and you can see that there are nice interrelationships among these bytes, and these interrelationships essentially result in reduction of the entropy. But then the question is, how do you automatically find them out? So we try to kind of automatically find them out by the following steps. So we try to kind of capture the DFA algorithm by essentially a set of fault distinguishers, which are constructed over the XOR differentials, as I mentioned. And the objective is to come up with an algorithm which is able to evaluate the distinguisher. But note that when you're trying to evaluate this distinguisher, you need to make the key, you need to make guesses on the key, but it is important that the key guess should be less than the exhaustive key guess. So therefore, in order to do that, we need to develop a suitable strategy. And finally, we are left with the remaining key space. And this remaining key space is also an important parameter to evaluate the quality of your attack. So what we develop is a few phased steps in this flow. The first phase is to try to find out what is the distinguisher. So the most important step to find out the distinguisher is to perform several fault simulations and then to find out that whether the entropy is really reduced. So how do we do that? So we try to kind of divide this into two cases. In the first case, as you will see, that sometimes these bytes are not related. That means they are statistically independent. So if they are statistically independent, then when we are performing fault simulation, we often find that certain bytes do not take certain values. So we find that although the correct range of a byte value should be, say, between 0 to 255, but it exhibits a reduced range in the fault simulations. So this shows that there is a reduced entropy. So there are certain classes of attacks which falls into this category. The other case, which is also very prevalent and more seen, for example, in ciphers like AES, is where these bytes are statistically dependent. So for them, we try to find out a mining operation. We adopt a data mining strategy. And the objective of this data mining is to come up with these dependencies, which essentially again imply that there is a reduction in the entropy. So here is an example to show you the first case. For example, there is an impossible differential that we identify for AES when the fault is induced in the input of the 7th round. And as you can see here, the highlighted state shows certain byte values, which never takes the value of 0. Because of the fact that it never takes a value of 0, we find out that the overall entropy reduces from 128 to something which is 127.9, which is enough to lead to an attack. So the second case, where essentially I've got correlated variables, are again shown here, which is the classical DFA for AES. And again, using the data mining, you can find out these interrelationships, which essentially shows that there is again a reduction in the entropy. So finally, you also need to evaluate this distinguisher by a key guess which is lesser than the exhaustive key guess. And in order to do that, we apply a graph-based abstraction of the cipher, which we called as cipher dependency graph, or CDG. So in the CDG graph, or for this formulation, every node is a bit from the cipher state. And then we try to kind of indicate links across these states, which are essentially created by various operations in the cipher. So for example, there could be a substitution box, there could be a key XORing, there could be a permutation. So this essentially creates causal dependencies among the bits. So this is something, a pictographic demonstration of, this is a pictographic representation of that, where you can see that these are the circles here represent the various state bytes, the state values, and the relationship shows that there is an operation which binds these byte values. So finally, using these blocks, you can essentially realize or represent the cipher. And this is one of the inputs to our tool. So we build this graph abstraction and then perform a graph analysis of this. So basically, we perform a traversal of these graphs and come up with some important parameters. For instance, if you want to so this is an example of the cipher called present. And if you want to kind of look into, for example, these bytes, you can see that you need to kind of, guess some key bytes. So these key bytes are shown by these dangling red circles. And you can imagine that if you need to kind of guess this input blue circle, then you need to make, say, guesses of 20 key bytes, or 20 key nibbles, which are needed in order to guess this particular input nibble. So the graphical abstraction helps us to come up or find out certain important components, which we essentially define in the paper, which are called as key sets, variables, variable sets, variable group, and maximal independent key set. So in a very nutshell, these parameters stands for, for example, the variables are the individual key bit values or the state bit values. The variable set stands for some like interdependent variables. The variable group essentially is composed of the variable sets. And finally, you will find out that the graphical traversal or graphical abstraction helps you to understand certain independent components in the in the key bits, which we call as a maximum independent key set. So understanding these parameters helps us to come up with estimation of the complexity of the attack. So for example, we find out what is the effective key size, we find out what is the remaining entropy in the key space, and essentially try to quantify the quality of our attack. So with this background, we will be trying to give you a quick demonstration of our tool. So we start with the fault attack on AES, where the fault has been induced in the 9th round of the cipher.
Hello everybody, I'm Shayandeep Shah, and I'm going to present a couple of demos on Default tool. As we have already mentioned that the tool checks two inputs. One is the fault simulation data, and the second one is a cipher description file. So let's begin with the fault simulation data. Without loss of generality, we are assuming AES cipher and a 9th round fault injection on that. Now, in X-fault nomenclature, the cipher execution is defined as a sequence of states. This fault simulation data is organized as such so that each of these files here represents the input of such states, which are basically input of each sub-operation. So by sub-operation, for example, I mean AES have 4 sub-operations: sub, byte, shift, row, mix, column, and add round key. And the input of each of them for several fault values, plain text, and key values are dumped here in this way. So this part of data is important to us. So if I take each of these rows, they have 16 values. So they represent 16 byte values of an AES state. And we can see there are some non-zero values where the fault has propagated, and there are some zero values where the fault has never been propagated, and so on. So the next input of this tool is the description file of the cipher, which is given as follows. Now in this file, first we provide some basic information regarding the cipher, the name of the sub-operations, and so. And the sub-operations are defined in this begin block, end block structure usually. So we have one, so how the S boxes are defined. So since the AES have 8 × 8 S boxes, so bitwise there are 8 bits. So we define it like this: each bit is dependent on 8 other bits, and so on. So this is basically an abstract representation, and in this way we can define all 16 S boxes, which comprises the S box layer. Then there is shift row, which is nothing but a bit permutation or byte permutation. We can break it in bit permutation for representation. The mix column, another operation where each output bit depends upon 32 input bits. And finally, the add round key, where each key bit is represented by these number after this plus sign. Most of the ciphers can be defined in this manner. I mean, we have found all contemporary ciphers can be defined. And finally, we define the round structure of the cipher in this manner. So now let's start the execution. So it requires the input file. So let us first do the fault injection at the 9th round, maybe at the beginning of the 9th round of the cipher. We are transferring the corresponding simulation file, and we have to select the cipher 2. Now the distinguisher identifier step is running here. It is analyzing the data using data mining operation and a couple of other steps, and the result is ready. Now let's see what the result says from here. It says that full state cannot be recovered, but only a 32 bit of keys among the total 122 bit has been recovered. This is common because we have injected the fault at almost the last round, basically the penultimate round, so the diffusion of the fault is incomplete. and that doesn't reach 96 bits of the key. So among these 32 bits, while I'm recovering the key, the evaluation complexity is 2 power of 32, and the total remaining key space size, including this 96 bits of key, is 103. That is the complexity, the remaining complexity for this 32 key bits is roughly 8. That is 2 power of 8. So this attack reduces the complexity of 32 bits key, the search complexity for 32 bits key, from 2 to the power 32 to 2 to the power 8 with an evaluation complexity of 2 power of 32. Now let's see some other results which will help us to better understand that. So as I've already mentioned, the tool actually discovers attack based on distinguishers. So for each attack, there are one or more distinguishers associated. For this specific attack, we have only one distinguisher, and our tool actually figure out and dump that out. So if you see this distinguisher, it has an evaluation complexity of 32, and as I was mentioning, it is reducing the key space to complexity of 2 power of 8. So that is here. The distinguisher structure is defined in this way, but most interesting part is this variable set where 4 variables, so distinguisher has 16 variables, byte variables of course, so 4 of them are associated and together they are taking 255 values on it. So that is why this state is working as a distinguisher. Now we have some other information as well to help the Cipher designer, which is kind of auxiliary from the tool, but it can be always generated. So if we see the corresponding CDG file, so the CDG file looks like this. The first thing to observe is that it has 16 independent components. This complete graph structure here represents the S-box. So the top layer is the distinguisher. The dangling nodes here are representing the round keys. So this represents the last round key. So one can see that with each byte of the distinguisher state, there are 8 key bits associated. And according to the structure, we have to actually combine 4 bytes together to actually get the entropy reduction into the attack. So in this picture, we have to combine 4 such subgraphs together and corresponding to 4 variables. And that makes a distinguisher evaluation complexity 2 to the power 32, because 8 into 4, 32 qubits has to be guessed simultaneously to evaluate this distinguisher. And that gives this complexity figure. And from the property of the distinguisher, we can see the remaining key complexity becomes 7.99. So that's how this attack works in general.
So with this, so this is the attack that works when the fault is at the input of the 9th round. So likewise, the optimal attack, as we know for AES, works when the fault is at the input of the 8th round. So the tool also helps to identify that.
In this example, we'll be looking at 8th round fault injection attack on AES. That means when the fault is injected in the 8th round of the AES cipher. So let's begin. First, we transfer the data, fault simulation files. Next, we choose the cipher file for AES. Here, the distinguisher identifier starts. So note that this line, I can think entropy can be reduced further. So with that, the result is complete. So in this case, the distinguisher evaluation complexity is 32. That is the maximum exhaustive search complexity for evaluating the distinguisher is 2 power of 32. And end of the day, the remaining key complexity becomes roughly 8. That is, the key space of AES reduces from 2 power of 128 to 2 power of 8. There is no case of incomplete diffusion here. Now, this is probably one of the most famous attacks that people talks about regarding AES. And here let's see how the attack has been figured out by the EXP fault. As we already mentioned, EXP fault may require multiple distinguishers to perform the attack. That is quite common in any DFA attack. So in this case, there are two distinguishers. So let's see the first one. So this distinguisher reduces the key complexity to 2 power of 32 roughly, with a distinguisher evaluation complexity of 2 power of 32. Now, if we look at the corresponding CDG graph, is like this. So once again, there are 16 components in this graph, and according to the distinguisher structure, where we can see there are 4 variable sets formed with these 16 variables, we have to group them in chunks of 4, and accordingly we require key guess complexity of 2 power of 32 for each chunk, and we can evaluate the distinguisher and reduce the complexity. So there are total 4 chunks, each having complexity 2 power of 8, which gives us a complexity roughly 2 power of 31.97 or 2 power of 8. So that's the first step of that chunk. But as we have already seen, that the attack says that it can reduce the complexity further. So let's see how. It is clear because there is another distinguisher. Now this distinguisher has an evaluation complexity of 2 power of 32 once again. It reduces the complexity to 2 power of 8. One can see that this distinguisher has 1 variable set, and that explains the complexity of 2 power of 8. Now, when we look at the corresponding variable set, sorry, CDG for this distinguisher, this is around 32. It's quite complex, right? So one can see that several key bits are associated. Here in this, here there are some dangling nodes, here there are some dangling nodes, but these key bits we need not to worry about because they get cancelled out due to the differential nature of the attack. There is no other layer remaining, but these key bits, these are the last round key bits, as we can show that actually we have to make a guess on all this 128 bit of keys at the last round. But we have already reduced the complexity of this last round key to 2 power of 32. So once again, our complexity becomes 2 power of 32. And eventually we can reduce the complexity of the entire 128 bit key to 2 power of 8. And that's why we get this complexity figure, which is quite consistent with the existing theoretical results. And so far, this is the most optimal attack found on AES, according to the literature. So thank you for listening.
So these are the two important demonstrations that we had to show how the tool works. And finally, there is a demonstration of a new fault attack on a cipher called Gift. And we show a quick demonstration of that.
In this demo, we'll look at a block cipher Gift, which is proposed in probably 2017. And this is a quite lightweight block cipher. And as a result, it has been involved in several authenticated encryption design, and some of them are currently finalist in a recent NIST call for lightweight cryptography. So due to its importance, we have chosen this cipher for our analysis, and as we'll see, it will give us some nice exotic results. So let's see. First, we have to transfer the data. So there are several rounds where fault can be injected. We have chosen a round 25 in this 28 round cipher. So in our previous experiments, we found that this round is one of the optimal fault locations, which is analyzed with this tool, of course. Now let's go. This time we are choosing the first entry and the distinguisher identifier in this process. Just to give an introduction of Gift, it is a bit permutation based cipher. That is, it has no MDS layer. So it has only S boxes, add round key operation, and bit permutation. And each round actually adds 32 round keys. And each S box output here, where the add round key operation is being performed, for each S box, which is 4-bit S box, there are 2 bits, 2 output bits, which are XORed with key, and rest of the 2 output bits are left. So the overall structure has very low complexity in terms of XOR gates, and that was one of the goals. Now the result is already there. We can see that here also we have reduced the key complexity to 72 bits to say 56 bits, because 56 bits has not been recovered, and the information about 72 bits has been recovered. The evaluation complexity is 8, and total information about 72 bits has been reduced to 2 to the power 11. That is 67 minus 56 gives us. So now why such results? There is no incomplete diffusion, but still we cannot recover certain keys. The reason is that GIFT has a very nice structure in terms of its key schedule. Each 4 consecutive rounds of this cipher uses completely independent keys. So we have total 128-bit key, and 32-bit keys are used in 4 consecutive rounds. So if we attack one single round of GIFT using this technique, it is not sufficient. We have to also get information about inner round keys. The last round key recovery is not sufficient. So standard approach for this is to get information about the last round key, and then remove the last round key, get for the other round keys, and so. And we also roughly followed that approach in this tool. But the thing is that the fault injection at 25 round actually leaks information about several round keys, not only the last round key. And our tool efficiently utilizes this information. Let's see how. If we go for the attack anatomy, we see there are 3 distinguishers. Let's open up the first. So the first distinguisher is like this. If we just go back to the CD file, we'll see it looks like this. Once again, there are several subcomponents, and according to the structure of the distinguisher, the tool actually combines 4 of the subcomponents, requiring 8 key guesses simultaneously. So these dangling nodes are the keys. So there, if I combine 4 of them, there will be 8 key guesses, which gives us a complexity of 2 power of 8. And after this step, the key complexity reduces to 11.53. Is 2 power of 11.53. And this is for the last round keys. For the last round, 32-bit key. But the attack can proceed further, and there can be other distinguishers as well. To get that, there is another distinguisher forming here, which also have quite low entropy. And this distinguisher is being formed at this point. Notably, this distinguisher have an evaluation complexity of 2, and it has a remaining key space complexity of 0. That is, it's unique. It recovers unique. So if we look at the corresponding CDG file, we can see that structures are quite complex. Now, how come the distinguisher evaluation complexity is 2? Because the tool assumes that it has already recovers the last round key, some information about the last round key. So for each of these choices, 2 to the power 11 choices that we recovered there is a unique choice for the penultimate round key, whatever it can recover, and the evaluation complexity for that part is 2 power of 2, which is lesser than 2 power of 8. So in this way, we can also get the information about another round key, some information about another round key, which is recovered by this distinguisher, and also with similar complexity. So overall, the remaining key case complexity, the maximum exhaustive key search that we require for distinguisher evaluation is 2 power of 8. The rest of them are 2 power of 2. And the remaining key complexity remains 2 power of 11, because for each of these 2 power of 11 choice, we can recover unit keys. So the tool helps us to go through such very complex pattern of key recovery, and it gradually builds up using its distinguishers and so that we can actually write down the attack codes quite efficiently and figure out what's going on. Thank you.
So that that ends more or less the demonstration from our side. So just to summarize, EXP fault is a fault analysis tool and we expect that we can provide support for new Cipher constructions. We are also trying to build support for like analyzing countermeasures using tools which we called as ALAFA and DLFALAT, which is a deep learning based analysis tool, where we try to also inspect the countermeasures and come up with some t-test and deep learning based methodologies to understand whether your countermeasures are good enough against fault attacks. So if there are any questions, we would be very happy to address. And of course, our emails are also provided over here.
Thanks. So I see that some people raising some question, and Say and Deep already answered those questions.
Okay, so I'm unable to see those questions because I guess I have to stop sharing to see those questions probably.
Yes, but it's already been answered by Say and Deep. So there are actually one more question. How would you using deep learning for fault analysis?
Okay, so maybe yeah. So basically, just to answer that, so the approach that we are trying to take is that we are trying to basically like, as you can see here, the like the various differentials, and you can see that one of the reasons why these attacks works is because these differentials have got interrelationships. So what we try to essentially do in a very broad sense is like to train some machine learning tools or deep learning tools and try to see that whether you can distinguish it from a random distribution. So the idea being that if there is a distinguisher available, then that can be potentially utilized to develop an attack. So we try to develop a framework through which we can not only analyze the ciphers, but also try to analyze their implementations with countermeasures.
Okay. Okay, so due to the time limit, so we will move into the next presentation. Thanks, Debdeep. Thanks, Sayandeep.
Thank you, Professor.
Thank you all. Yeah.
Thank you.
Okay. So again, if you want to learn more about these tools, please go to our CAD for Assurance website. So our second talk is on the automated hardware Trojan benchmarking. This is a very hot topic because everyone is working on Trojan detection. Everyone is asking the question, where is the Trojan benchmark that we can leverage? So this presentation actually introduced us that where you may find the hardware Trojan benchmarking. So Jonathan and Patanjali.
Thank you, Dr. Jen. Good morning and welcome to today's demo session. In today's demo session, we'll be discussing the tool for automated hardware Trojan benchmarking. Next slide. So the challenges of manufacturing electronic devices at nanometer scale has motivated the semiconductor industry to adopt a globally distributed manufacturing process. While this distributed manufacturing process entails considerable economic benefits and it improves design productivity, it does raise some concerns. The primary of these concerns is the degree to which the manufactured device can be trusted. Next slide. Of these various trust issues, the most prominent and the well-studied one is the issue concerning a malicious or an untrusted entity in the supply chain making malicious alterations to the design. These malicious alterations are also referred to as Trojans in common parlance. The reason why Trojans are a serious threat is that the attacker can introduce these modifications at virtually any design abstractions. The malicious modifications can be made at the RTL level representation of the design or by an untrusted entity in the SoC integration phase or by manipulating the design tools or at the foundry level where the design is sent for fabrication and assembly. Thus, there is a critical need to protect the supply chain against the threat of these Trojans. Next slide. So typically, a Trojan consists of two major components, a trigger and payload. Based on the nature of the trigger and payload, Trojans can be classified as combinational or sequential Trojans. Next slide. So over the years, there has been considerable interest in the research community against mitigating the threat of these Trojans. So there are, in today's literature, there are thousands of countermeasures that can be deployed at various design abstractions. There are tools that can serve as countermeasures at the IP level, or can be used by the design house, or can be used at the at the CAD tool level or at the foundry level. However, the problem of identifying the right tool for a given use case still remains an open and interesting research problem. Next slide. So the major reason is there are two major reasons that affect the applicability of a Trojan countermeasures. The first is that the analysis or the observations performed by these countermeasures could be derived from a limited set of benchmarks or by a limited set of Trojan samples. The second is that there is no standard metric that can be used by the designer to evaluate these various tools on an apples-to-apples comparison. Thus, there is a need for a framework that addresses these limitations. To address that, we propose the automated hardware Trojan benchmarking suite, which John will now describe. John?
Thank you. So, to that end, we went ahead and we created a software tool for automated Trojan benchmarking. So we designed methods and algorithms for inserting any number and any type of hard to detect Trojans into a flattened Verilog netlist design. So we ensure two major components of the Trojan. One is that we ensure that for a triggered Trojan, that the triggering conditions are valid so that they can be triggered in field. And two is that the malicious effect or the payload is observable. Without any of these two conditions, the Trojan is essentially dead logic. So with this automated Trojan benchmarking tool, we allow for dynamic and unbiased benchmarks, which are now representative of the entire Trojan population space for a given benchmark instead of these point benchmarks for Trojans, or if your design is not on TrustHub, then you won't have any reference for Trojan insertion. So our tool is called TRIT ASIC, or Trojan Insertion Tool at the gate level abstraction. So next, I want to highlight 3 use cases for such a framework. So first, because we have the capability of generating a large number and distribution of Trojan inserted designs, we can enable powerful IP trust verification and big data analytics in the form of machine learning. So now with this tool, we have the ability to create effective training and test sets for ML-based Trojan detection techniques. Second, with such a framework, we're no longer limited to the static and fixed number of benchmarks which are previously available. By creating random, diverse, and statistically significant Trojan data, we can now achieve an unbiased coverage estimation for any proposed trust verification scheme, which in simpler terms boils down to essentially how many Trojans can my proposed technique detect. And then finally, with automated Trojan benchmarking tools, we can enable trust-aware design flows. So now an IP designer can incorporate TRIT ASIC throughout the different stages of their IP development to ensure that the design is protected from Trojans, and can also modify the design accordingly to cover any Trojans that were identified through the TRIT flow. So now here's the overall flow for TRIT ASIC. So the first thing we do is give in the flattened Verilog IP, and along with a bunch of user configurations, we go ahead and we create a hypergraph representation of the netlist. After that, we go ahead and we perform a topological sorting of the combinational gates, and we do this one so that we can simulate, and two, that we can ensure that any Trojan that we insert does not form any combinational loops, which would be an immediate red flag in most CAD EDA tools. After that, we go ahead and we calculate the signal probability of logic 1 and logic 0 for every single net. Now that we have this, so the user will provide a threshold theta, which is essentially a threshold for the signal probability, and any net with a signal probability 0, 1 that are below this threshold is a potential candidate net. Now we start to randomly combine these subset of candidate nets to form sets of triggers. Now, once we have this set of triggers, doesn't mean that all triggers can achieve their rare value at the same time. So to do that, we go ahead and we validate these. Specifically, we use Synopsys Tetramax for this portion. And then we go ahead and now we have a set of valid candidate triggers. And which now that what's done in parallel is that we go ahead and we find potential payloads. So we make sure that all payloads are observable. Again, this check is done through Tetramax. And now once we have this set of candidate triggers and candidate payloads, we go ahead and start to create sets of Trojans, again, ensuring that the topological ordering is not violated so that no combinational loops are formed. And then finally, with respect to the rest of the parameters that the user provides, we can go ahead and we can construct a Trojan and insert it into the design. So another high level overview. So TRIT ASIC, we have several different user parameters. So some of which are the number of Trojans to insert per design, the type of Trojan to insert per design, and then Trojan features such as the activation probability. So to this end, with this tool that we've developed, so it was published in date 2018, and we have uploaded nearly 1,000 Trojan inserted ISCAS, Trojan variants of ISCAS 85 and ISCAS 89 designs, and they're both on TrustHub and CAD for Assurance under TRIT TC and TRIT TS. And then this work has also directly contributed to ML-based Trojan techniques. So now this gets me, so here's the overall flow again. And so now I'll be going over the live demo portion. So let me go ahead and momentarily stop sharing and switch my screen around. All right, so I have two terminals open. So first I'll go over the interface. So we have a Python wrapper for this particular tool, and this takes care of input sanitization, and it'll set up the environment, and then it'll finally make sure that you invoke the correct tools and also our executable. So I will note that we have dependence on at least two industry tools. So one of which is Synopsys Tetramax, and then the other is either Cadence Jasper Gold or OneSpin. So here is essentially the user parameters that a user can provide. So one is that we take typical design information. Obviously, we have to provide the flattened Verilog netlist. You provide the top-level module name. Now, in terms of standard cell libraries, because we are working on the gate-level netlist, we only support two standard libraries as of yet. One of which is the LIDA 250 nanometer, which some people are seeming to have a difficult time to get a hold of. And now we also support Skywater PDK, which is an open source PDK by Google and Skywater. So we also support that standard cell library. It's a modification of it. We just changed slightly the names. All the parametric values are the same. Then we take clocking information if needed, reset, and activation edge of the reset. And then you have to specify whether the circuit is combinational or sequential. Now we have this optional feature here for the design to provide via the Tetramax SPF file. This is for defining the scan chain if you have a specific scan structure or partial scan design. Alternatively, you don't have to provide this, and we just assume by default that all flops are in a scan chain. Now, the next set of parameters are for the Trojan itself. We support two main effects of the Trojan, either denial of service, which you would provide DOS, or leakage. So denial of service Trojans would essentially alter a payload signal, whereas the leakage would then leak the payload signal via primary output or through some side channel. And now the type, so this essentially is the body of the Trojan, you can think, or the structure. So we have a library of combinational templates, sequential templates, or you can provide your own template, which has to be in a specific format, which I'll get into later. Then the activation condition. So we support triggered Trojans and then this always on Trojan, but the always on Trojans are only, we only support the leakage effect because it doesn't make much sense to have an always on denial of service because that would just be a very noticeable bug. Then we define theta, which is the signal probability threshold for this particular design, followed by the number of triggers. If it is a trigger Trojan, how many triggers do you want in that Trojan? And then we have n rare, which is essentially the subset of these triggers that are below the threshold so that you can combine both rare and potentially non-rare trigger nets for your fan-in for the Trojan trigger. Followed by, now you can, so this is an optional feature, the next three. So the first one, payload, is essentially you can specify specific payload for a design, whether it's you want to perturb a state bit or you want to leak a secret key. Now the difference between the payload and the secret parameters are that the payload, so the payload for denial of service is whatever signal that's going to be perturbed, whereas the secret will be leaked through the payload. So you could specify that a key is leaked through this particular output. Next, we get to the template. So this is a user-defined Trojan template. And then you can specify the number of Trojans per circuit. So if I want to insert 2 Trojans in the design, and then the next parameter, n files, is essentially how many of these Trojan inserted benchmarks do I want to create. So you can create these in large volume. Now, these next 2 flags, so the trit flow, there's essentially, we've broken it down into 2 main components. One is the generation phase and one is the construction phase. So these can be done separately. So the generation phase can be done, essentially one time where you generate a Trojan population for a given circuit. And then once you have a sufficient number of Trojans, potential Trojans, you can go ahead and concretize them through the construction by providing the construction flag, and we'll go ahead and insert, then we'll construct and insert the Trojan depending on this parameters that the user has provided. The next couple of flags are specifically for if you want to guarantee that all triggers are unique among all generated benchmarks. The random one is if you don't care for any of the specified triggers, if this will essentially override n trig and n rare, so it'll just randomly select the sim flag. So because we use simulation for calculating the signal probabilities, and simulation can take some time, we offer this as a flag. So you only have to do it one time per design, and then we offload all of the probabilities so that we can improve the performance. And then I would like to just highlight the last one here, so this verification. So we do one last verification. So once we insert, this is where we use either Jasper Gold or OneSpin to just double check that even without scan chain, that the Trojan can be triggered. So with that, I will now go over one example. So first I'll go over a generation example. So here I have a script already. So here I'm invoking the tool on this ISCAS 89 benchmark. I'm using the Skywire library. And because I'm going to be doing the generation phase, these other parameters don't matter so much, the like effect type and stuff like that. What really matters is this theta, this n trig, and this n rare, and then this effort. So this effort level is essentially how many times I'm going to try to generate a valid population. And that's like a maximum effort because we are randomly combining, and then the subset can show up that none of them are valid. We want to essentially increase the effort up until some period that you're willing to wait. And then finally, we pass this -g and -sim flag because we need to go ahead and generate that. So I will now run it. So we go ahead and, as you can see, we create the graph, and then it does topological sorting. and then it goes, and now it's applying the simulation. So here's just a random 100,000 test patterns. And then once that's done, we go ahead and now it invoked Tetramax. So it also provides some graph statistics. So this is the number of vertices, number of flops, so on. And then it gives you information based on your threshold, how many nets were candidate. So then that's the pool of nets that it tries to essentially come up with sets of 5 different trigger nodes. And then from this run, it was able to generate 118 unique Trojans, and they were stored in this Trojans Skyward. So let's go ahead and take a look at that file. So here, the way that we store them is essentially the trigger net, its rare value, and then this goes until all of the triggers, and then finally the last net is the payload net. And then here you can have, so because we're randomly combining, there is a situation where you can have more Trojans than what the unique number says, and that's just because there may be repeats. So now that I have this Trojan population, I can go ahead and construct the Trojans. So first I will show, so now the construct, all I've done is essentially, it's the same parameter that I've passed previously, but instead of passing the -G and -sim, I just have this -C, which is the construction flag. And I'm verifying with Jasper Gold, and then I'm inserting this template Troj com5. So I will go ahead and show you what that looks like. And then, so this is just a very basic Trojan, which is just a NAND fan in followed by a NOR. So this is the final trigger. So it takes in 5. So you specify, this is the main skeleton, is that the inputs are in underscore. Then you have original keyword, payload keyword. The original is the net that will be perturbed. And then the payload is the output. And then here we essentially fill in all of the triggers to the specific template. So now with that, I will go ahead and run the construct script. So it's selecting from the 118, and then, oh, and I also forgot, I put for the number of Trojan inserted files, I put 2. So it'll insert 1 Trojan and it'll generate 2 instances of these designs. So I have a Trojan file S95 T000 and T0001. So these are located. So if I go ahead, there's this T benchmark directory, and this is where all of the outputs are stored. So now I have these 2 directories where my Trojans are. So each directory will now have a log file, and then finally it will have the Trojan inserted variant. So let me go ahead and show you what that looks like. So see, I have this log, so I'll go ahead and open up the log file first. Whoops. So every log comes with this same header, and then it'll tell you the number of Trojans that were inserted, the type, the effect. So this was denial of service. So it altered this particular signal, and then this was the activation condition. So these are the trigger signals, and then finally this is the Trojan body that was inserted. So now if I go ahead and I look at now the Trojan inserted net list, so now the Trojan is inserted all the way at the bottom. So if I see the top, this is the same, but we've just added this prefix of what the original design was. And then now if I go all the way to the bottom, this is where the Trojan is with now the corresponding gates. And note that even though we name the gates Trojan just for ease of visibility, but this can easily be remedied if you wanted a pure unbiased way where you don't know where the Trojan is actually inserted. So now if I can go ahead and I can show one more example. I'll go ahead and do a different template, a sequential Trojan template. So I'll go ahead and change that to, this is FSM, and I'll just go ahead and change the number of files to 1. Whoops. And then now I will go ahead and rerun it. So now it's inserting the Trojan. So here's where this is a good example of it is inserting, it's trying different of these Trojans that were available, but some of them are failing. So the reason why it would fail, even though we validated it, is because we assume full scan. So when we're doing the initial verification of the Trojan, it could be that the specific scan-in was never achievable in field. So that's where this final check is. We go in and with this Jasper code, we make sure that from the primary inputs through in-field operation that the Trojan can be triggered. So now it has overwritten the S953. So if I go ahead and now look at the log file, so it is very similar. It's selected a new subset of nets, and then now we have this. This is essentially, this is a two-state FSM with every time that the Trojan triggers, it'll move the state machine forward until the final state, and then it'll go ahead and trigger the output. So that is the demo portion. So I'll go ahead and go back to the slide deck. So these are the references that were used, and then we'll gladly take any questions.
Thanks. So Jonathan, can you see the Q&A session? There are 5 questions there.
Let me see.
I can read it for you.
Okay,
if you stop sharing your screen, you should be able to see them.
Okay, so
okay. Okay, maybe you need to stop sharing it.
Okay. All right. So the first question is, should ASIC approach limited by the availability of the user specification to create hardware Trojans? So we have, in terms of limited for the templates, we have a bunch of predefined templates already available for the user to use. So they are limited in that sense, but we can also support any template that you provide as well. Next question is how to topologically sort a sequential circuit. So that, because we assume full scan, we make the problem much easier, and the all of the scan flops are essentially primary inputs. So that's how we deal with that. Have hardware Trojans been inserted into IC designs from OpenCore, LibreCore, which are larger? So we have internally, yes, we have done designs such as AES and several of the crypto cores that are available on OpenCore, and some of the smaller ones like XT and Simon. We plan on uploading more Trojan inserted variants to CAD for Assurance and Trust Hub with a larger variety of, as you mentioned, larger designs and more robust designs from open cores. on both of these websites very soon. Next question, what is the difference between SOC level and IP levels? Trojan sounds like the Trojan assertion is still inside an IP. Yes, that's a very good question. So for this particular tool, this is an IP level Trojan assertion. Now the difference for SOC level would be fundamentally at the communication between IPs. So that would be leveraging that sort of communication there. Two, can the Trojan assertion be cross-module, like the triggers? So for this particular IP, so because we only take flattened designs, so if you flatten the entire design, it can be, there's a chance that it could be cross-module. But if you want it from like a typical module RTL level perspective, then the tool currently does not support that. But that is a very good point, and that lends itself more to the SOC level Trojans. And then besides DOS and info leakage, are there any other payloads? Currently, no. So we don't have any other of types of payloads other than those. And then the next one is, can TRID ASIC approach insert hardware open core, which are much larger than ISTCAS? Yeah, so this was, I think, another question that was similar to the one I previously answered. Yes, that we have tested on much larger IPs, and we don't have much of a scalability issue, and it is also mitigated by this sort of piecemeal approach that we took. And right, that a lot of open source designs don't have adequate hardware security specifications. So it would be interesting then to insert Trojans in them.
Thanks. It's very efficient in answering all these questions. So if the attendee have more questions, so feel free to contact the author, the speakers, and again, the tools, or at least the binary and some demos are available on the CAD for Assurance website. Please do check back on the website frequently, because we are keep on updating the website with more and more tools being involved. In the meantime, if you have any tool which you believe that it's worth advertising or worth sharing so that other researchers can leverage the tool, please do not hesitate to contact us, or we have a link on the CAD for Assurance website that you can just click a link, you can submit it, and we will get back to you very soon.